You have two tasks to solve rigid body equilibrium problems. Set the vector sum of the forces equal to 0, and set the vector sum of the torques about any point of your choosing equal to 0. If all the forces acting on a body are within the xy plane, then we only need to worry about the z component of torque. If we have forces acting in 3 dimensions, we would have to verify that each component of torque is 0. But most problems will be nice and only have forces acting in x and y, and so you only have to verify these 3 things. The sum of the forces in the x direction equal to 0. The sum of the forces in the y direction are equal to 0. And the sum of the torques about some point equal to 0. And that point will be, the torque will be along the z-axis there. So those are the 3 things we need to verify. So this is a kind of a new category of problems, and so kind of like we've done in the past, I'm going to go through some strategy. Let me put this up big on there. I'm going to go through strategy for solving these types of problems. Move that up. And we'll just read through this. All right. So identify as, if you're given a problem, you're not told, oh, this is an equilibrium problem, like say on the final exam. And you need to know, does this stuff apply? The first and second conditions are that the sum of the forces are equal to 0 and the sum of the torques are equal to 0. They're applicable to any rigid body that is not accelerating in space and not rotating, right? And so if you're given a body and you say, oh, this thing's supposed to be rigid, it's supposed to be stuck in space, not accelerating, and not rotating, then you know that it's an equilibrium problem. All right. So first, as always, we're going to sketch the physical situation. We're going to identify the body in equilibrium to be analyzed, sketch the body accurately, and don't represent it as a point this time, because now we're taking the torque around each different points. Right? So we're going to include the dimensions. Then we're going to do a free body diagram. We're going to show all the forces as usual acting on the body. But different from this is you're going to show the point on the body at which each force acts. So in the past we've done free body diagrams, separate ones for each body, and each body is reduced to a point. We're not doing that anymore. You're doing a free body diagram of the system as a whole. And so you'll see in this example problem that we do next how that works. You're going to choose coordinate axes, as usual. Specify the positive direction for each axis. And then you're going to specify a positive direction for the rotation of torque, right? It's either going to be one way or the other. One of them is going to be positive, one is going to be negative, doesn't matter which way, it's just so that you can be consistent with yourself. And then we're going to choose a reference point about which to compute the torques. And this is a crucial one because you can really save yourself a lot of work. So you can eliminate from your torque equation any force whose line of action goes through the point you choose. What this means is, if you remember, the definition of torque is just R cross F, right? R being the distance away from the axis of rotation. And so if we have some force acting at the axis of rotation, right? We have some force acting at this thing. Well, R is 0 because there is no distance that it is acting away from the axis. And so this whole force provides no torque. So if you choose the point that if you choose your axis of rotation, right, the point to sum the torques about, at the place where most of the forces exist, then you can eliminate as much as possible. So if you have a force existing there, and there, and there, and another one there, and there, and then you have something acting over here, well, if I choose to sum the torques over some random point that exists here, well, there's a distance r there, there's a distance r for all of these, and there's F for that, F for that, F for that, for each one of these. So I would have to include 1, 2, 3, 4, 5, 6 torques that I'm summing about this random point so that we can see, oh, does it rotate this way or that way or not at all, right? But if we instead chose this point as the point, as our axis of rotation to sum the torques about, well, R is 0 for all of these. So the only one you have to consider is this guy. And in that case, of course, there would be a torque, because unless this F is 0, then there is some torque in this direction here, in this case. But so choose your axis of rotation wisely so that you can cut out as much work as possible. Nobody is counting, nobody's giving you extra points if you chose the harder way to do the problem, right? And then you execute. So it says, write equations expressing the equilibrium conditions. Remember that f sub x equals 0, f sub y equals 0, and tau sub z equals 0. And these are the sums of all the forces along those components and sum of all the torques, like we just talked about. And those are separate equations. So let's see. Yeah. Ignore the rest of that one. To obtain as many equations as you have unknowns, you may need to compute torques with respect to 2 or more reference points. Choose them wisely. That probably won't come into play, but we have that. And then evaluate your answer. So let's put this into practice. And let us do, let's see. Yeah, we talked about that enough. Okay, so let's put this into practice and do a problem here that is a classic physics problem and has a ladder leaning up against a wall. And we have some friction force from the wall on the ladder, and friction force on the ground, from the ground on the ladder, and we are trying to solve for some variables. Okay, so here's the problem. And there's also a sketch that goes along with it. So I'll put this here, and then the sketch right next to it. And go ahead and give it a read. How does that look for you? Oh, let me make this better. Okay, Sir Lancelot, who has some weight, is assaulting a castle by climbing a uniform ladder that is 50 meters long and weighs 180 newtons. So this is him over here. The bottom of the ladder rests on a ledge and leans across the moat in equilibrium against a frictionless vertical castle wall. So in equilibrium. So if this didn't come up within, the context of talking about equilibrium, you'd know just from that term right there. The ladder makes an angle of 53.1 degrees with the horizontal. Lancelot pauses 1/3 of the way up the ladder. And they give you, I guess we'll have to figure it out. So find the normal and friction forces on the base of the ladder. That's A. B, find the minimum coefficient of static friction needed to prevent slipping at the base. And C, find the magnitude and direction of the contact force on the base of the ladder. All right. So the first place to start is to notice some differences in this problem from what we have typically worked with. So first, the whole system is stationary, and so we can use the equilibrium conditions to solve for the variables it's asking for. Second, there are 2 bodies in this system, the ladder and Sir Lancelot, with 2 respective centers of gravity. Third, there are 2 normal forces acting on this system. Usually we just have one normal force. There's 2 normal forces here. There's the normal force of the wall against the ladder and the normal force of the ground on the ladder. So first we're going to draw a free body diagram of the system with both the man and the ladder in the same diagram. And that's different, like I said, than than we used to do with regular Newton's second law problems in lectures 4 and 5. The reason we can do this is because we now know how to compute the torque on the entire system about some point, and then more importantly, we know the entire system is supposed to stay rigid and stationary. If each body were moving independently, then we'd have to consider the motion of each separately again. But yeah. So let's draw our free body diagram. I'm gonna just move all this upwards. Maybe it'll stay in frame for a little while for you. Okay. So we have the ladder. It's different from our other free body diagrams because we're not just reducing it to a point, right? All right. And the ladder has some center of mass. I'll use white here. Ladder's center of mass is here-ish, right? And its weight is acting. This is the weight of the ladder, so that was 180, yeah, 180 newtons. Oops. Okay. You can say weight sub L for ladder if you want. And then there's Sir Lancelot, and his center of mass is going to be here. And his weight is 800 newtons. All right, what other forces do we have on this system? Well, we can, while we're thinking about that, we can assign a coordinate system. So the ground was here, and so I'm going to make this the positive x direction. Positive x. I'm going to make straight up positive y. Because there's not really many forces along the ladder here. So it doesn't really make sense to rotate, even though usually for diagonal things we'd rotate. This force is straight down, this force is straight down. We have the wall here, and there's a normal force of the wall perpendicular away from the wall. So there's normal force, I'll say that's N1. So that's also right in line with our x direction. And then there's a normal force here. Call that N2. That's of the ground on the base of the ladder. And then there's a friction force here. And that's static friction. And we don't know how large this one is, or that one. All right. So, oh, and then we have the angle here. I'll do this. This is, we'll call it theta, and it's 53.1 degrees, I believe. Yeah, 53.1 degrees. How does that look? Are things overlapping? That looks okay. I'll make it a little bigger. Okay. So that's our situation here. All right, and then we can write some dimensions on here, right? So we can write some dimensions. So they give you, what do they give you? The length of the ladder or something like that? Yeah, okay, so the length of the ladder is 5 meters. So I'm going to write this here. 5.0 meters is that full length of that blue ladder there. And with the angle on that length, we can figure out how high up that acts. We can figure out how high up each of these are. And I'll go ahead and write it out here. So this, the height from there all the way down to here, if you calculate, is 4 meters. And you'll see why this is relevant, but I'm going to write the distance here, that distance, yeah, do a bar. That distance there is 1.5 meters. This distance here is 1 meter. You see all that? Okay. So the reason we want to throw some dimensions on there, you might not, be able to predict or foresee what dimensions will be most helpful, but the reason we want to get some down is because we're going to be summing the torques around some chosen point, right? And so we will need those r vectors from our point. And so I guess you could start thinking about that now and then figure out the lengths, but just throw these down and we'll come back to them. So now, the thing to do would be to sum the forces in the x, sum the forces in the y, set those both equal to 0, and we can also choose a point for our torque and sum the torques about that point, right? Those are like the three things. So first I will sum the forces in the x. Let's just move on to this greenish color. Sum the forces in the x. In the x direction we have, if we call that positive, we have friction F sub s working in a positive direction, and the only other one is the normal force of the wall on the ladder, which we called N1, and we set that equal to 0. Alright, and so that pretty simply gets us that the we'll say F sub s is equal to N1. Alright, so those are equal. And then F sub y, what do we have in the y? We have the weight of the ladder, we have the weight of Sir Lancelot, and we have the normal force back up. So I didn't label them. Lad and weight of M for man. How about that? So this can just be L then. Alright. You could just skip right to the numbers if you want, but I like to keep symbols going. So we have N2 in the positive y direction, and then the rest are minus. So minus WL, and then minus WM. Ladder, man. We set that equal to 0. Alright, so that's all well and good. We have an equation here, we have an equation here. Actually, since these we know the numbers of, then we can just solve for N2 right now. So N2 is equal to the addition of these. So N2, which is one of the things we were trying to solve for, is equal to 980. Okay. So now, do we have enough just based on these two? Sometimes you do. Sometimes you do, but on this one we don't have enough. We have to sum the torques, because what we're interested in finding is N1, N2, and F sub s. So we got N2, so this answers one of the three things in part A, but we can't really use that to find these two, right? So we know that they're equal to each other, but there's no relation in this equation here to N2, so we have to go further. So now we have to sum the torques. So again, to sum the torques, it's always best to choose a point that makes your life easier. And so if we pick a point exactly where a force is acting, then that force isn't providing any torque about that point, because the r vector is 0. The distance from the axis of rotation to the point where the force acts, that's 0. So you want to choose a point where the most forces are acting. And with this system, let's go back to our free body diagram here. With this system, where are most forces acting? There's one acting at this point, one acting at this point, two at this point, and one way up there at that point. So this would be the best place to sum the torques. Moving on to torques, so I'll change to a new color. So we're going to choose this point right here at the base to be our point where we're summing the torques about. And that means that we don't have to consider this guy because its r vector is 0 via according to this axis of rotation, right? So this is the z coming into and out of the page. So we're looking to see if it's rotating this way or this way, right? It's not going to be rotating other ways because there's no forces in the z. And there's no z component forces, so it's not going to be coming back at you or going back into the page, right? So that's why torque is simplified a little bit. So we just have to figure out the z component of torque. Okay, so summing there, we have to say that the sum of the torques about that point, right? And so really that's the z component of the torque. We have the torque that is provided from these three things. We have the torque from this weight, making it want to go this way, and we'll define this way as positive torque. How about that? That way is positive torque. And so you have this way, that force making it rotate positive force, a torque, this one making it rotate in the positive direction, and then this one making it rotate in the negative direction. So this one better cancel out these two so that it's not rotating. So symbolically, what that translates to is the torque N1, lowercase n, plus the torque WL, the weight of the ladder, plus the torque of the man, torque sub m, tau sub m. So the interesting thing is that while this seems like there's a lot of trig involved here to find each torque, the messy stuff actually cancels out. So let me walk through what you would be doing traditionally. So torque, it's only the perpendicular component, right? So it's only the component of this force that is acting perpendicularly to this ladder, right? And so there's a component that is acting in each direction. Everything's shifted on you. It's a hot day, and the tracking electronics that track the headset and the controllers are overheating, so I got to give it a break every now and then. So things have moved a little bit on you, but it's the same stuff. So let's look at this one here as an example. So if we're talking about the torque that this is providing here, right? It's in relation to this axis, and so we have the r vector is here, the vector, the position vector from the axis of rotation to where the vector is acting. And then there's two components of this guy, right? So if we're talking about the force, it's only the perpendicular force that counts. So there's this force. This would be like n sub 1 perpendicular. And then there's this component, which is parallel. And this would be like n sub 1 parallel, right? And the one that is acting, the one that counts for torque is only this guy, right? So you can't just take the r vector, the distance from the axis of rotation, and multiply it by n1. That's not the torque. It would be this component. And you have that situation going on for each of these. They're all kind of at this weird skew angle, right? So this one, you'd only be caring about the perpendicular component and the perpendicular component of that one. But I'll show you that some of that cancels out. So, pull my notes back over here. So let's make a new, no. Let's see. Well, so this perpendicular component here, this angle here is the same angle as our angle for the ladder. Can you see that okay? Yeah. This angle there is the same angle as for our ladder, so 53.1, right? And so if we wanted to get this, we'd just take sine of this angle because, right, that's the same length there. So sine of this angle. So we would have, let's work over here. We would have n1 sine theta, or 56.1, or 53.1. And that's equal to n sub 1 perpendicular. That's that component that we want. This is our F in R cross F for this torque, right? Okay. And so we have that we have that sine of I'll just write it out. Sine of 3.1 is equal to 4, which is here, right? So it's the same thing. Sine would be opposite over hypotenuse, so 4 over the length of the r vector, which is the distance from the axis of rotation to this thing here, right? And if you solve for r, so if you solve for r, that means r is equal to 4 over sine of 53.1. Okay. And what we're trying to do is we're trying to find the torque of n1 about the axis that we chose, right? And torque is r cross f, but if you've already found the perpendicular component, you could just say r and then the perpendicular component of that force. So we're trying to do r times this value here. So that's what we can do now. We can say r is 4 over sine 53.1, and then this guy is up here, n1 sine, and I wrote theta up there, but I will write it fully out here, 53.1. And look at this, all the trig stuff cancels right out. And so the torque about that point, that axis, caused by this force N1, normal force of the wall and the ladder, is 4 times N1. So it all kind of cancels out. So we can go over here and fill that one in at least. So that's equal to 4 times N1. And then I'll tell you, for these guys, the same trick works. They're just causing reverse torque. And so the same trick works if you use this distance and consider this triangle and this triangle instead of considering this triangle. And so you can use this distance here, and it cancels out just the same. You can go through it if you want. But I'll go ahead and write it out. So it's going to be minus, because we have negative torque being provided by those guys. So minus 1.5 meters. And this time we have the value of the force. It was the weight times 180 newtons. Newtons, capital N. And then minus the other one. So that was for the ladder. And then this one here, we have minus 1.0 meters times its weight. The man's weight was 800 newtons. Okay. So hopefully you followed that. You can go about it the long way. It's just kind of nice. Things cancel out if you can see how that works. So we have the sum of the torques. We can set that equal to 0 because it is not rotating about that point. It's in equilibrium. And now we have equation for N1. And so we can solve all that and say N1 is equal to 268 newtons. 268 newtons. All right. And then we can use that to go back and plug it in for to solve for F sub s. And they were equal to each other. So F sub s, the friction force, static friction force, is equivalent to that. So it's F sub s is equal to 268 as well. So F sub s equals 268 newtons as well. And now we have solved for everything that it wanted, both normal forces, much smaller up here, and the static friction force. So then B asks something further about that static friction force. What does B ask? It says find the minimum coefficient, I'll put it back up here, minimum coefficient of static friction needed to prevent slipping at the base. So the minimum coefficient of static friction. So from the definition of static friction, we get that less than or equal to sign, right? So static friction less than or equal to mu sub s times the normal force. And in this case, we were writing lowercase, it's N2. This one, right? It's the normal force of the ladder on the ground. All right. So what's the minimum coefficient of static friction? Well, you can solve for that. Mu sub s. We'll say it like this: min is equal to F sub s over N2. And we have both of those values, and so mu sub s min is equal to 0.27. Unitless number, remember. So that's the minimum. Of course, if it were much larger, it would be able to keep the ladder in place as well. It's just asking for the minimum, and that is the minimum. And then C asks about the total contact force on the base of the ladder. That's just the force vector made up by the two components, N2 and F sub s, right? So there is some total force vector this kind of way on the ladder from the ground providing a component that is frictional and a component that is nominal, I guess. And so we're just going to use those two and find the magnitude of that. So the total force vector, we'll say F is equal to square root of the sum of the squares. So we have F sub s squared plus N2 squared. It's traditional way. And I don't remember which one was which, but we have one of them being 268 newtons. I think that was the friction force squared. And the other one is 980 squared. And if you compute that out, you get that the total force magnitude of the ground on the ladder is 1,020 newtons. It's noisy today. Everybody's going by. And you can find the angle from the horizontal that it acts at. It's not necessarily the same angle that the ladder is resting at. By taking the inverse tangent. So theta, this is theta of the force vector. I'll just do theta sub f. You're going to take the inverse tangent of 980 newtons divided by 268 newtons. And that angle, if you compute it out, is 75 degrees. So not the same angle that the ladder is at. It's a little bit more. Let's go back to our picture here. The total force vector turns out to be, if this is 53.1, total force vector here turns out to be something closer to like this, because it's a larger angle, it's 75. Not guaranteed to be the same. Okay, so that was that example. Thanks for bearing with me through the multiple times my device cut out there. There's another video coming up, so I'll see you in the next one.